my screen though.
Yeah, it's visible to us.
All right. Okay. Sorry for the minor inconvenience. Good afternoon, all. Uh, Today I'll be presenting on my final year project, which is on privacy preserving analytics. So let's talk about what privacy preserving analytics is about. So the problem is whenever you, let's say you go online and you subscribe to a service, and the service, in order for you to in order for you to give some results, it wants like certain data from you. So what it does, it asks for you data and it asks from multiple users, and it munches it together and gives the result for what you subscribe for. So that's basically an analytics system. And the problem with analytic systems is like privacy and anonymization isn't well implemented in them. So the natural cause of that is many users who are concerned of their privacy don't even participate in these analytic systems. So the goal of the project is designing and building a pipeline to randomize response collection, thereby making the database differentially private. So the two things that I want you guys to look into is randomized response and differentially private, which I'll be like talking further up in the slides. So the motivation is essentially privacy is a fundamental right, and machine learning is everywhere, which runs on analytic systems. So you got to take care of it. So the major components involved in this system are, the first is something called randomized response collection. So the idea of randomized response collection is like, let's say for a question, I could like the true answer could be like only one identifiable answer, but my system will just randomly change that answer and submit to the analytics system. An example to that would be a question, let's say like, do you like ice cream? So my true response would be yes, but the system will like with a uniform probability change the answer to either no or yes back again. So, but the point is that I can't uniformly change my true answer to something else. The problem with that is, in the end, the analytics system with 10 different users would only get the uniform distribution of what's been randomized by the system. So we need to introduce some sort of a bias into what's true and what's a lie. So for that, we introduced something called epsilon differential privacy. So this is like the technical definition to it. But on very simple essence, it simply means that the probability of me giving a true answer and the system giving out a particular answer versus another answer should be less than e to the power epsilon, where epsilon is a chosen value. So this essentially makes sure that there's like not one set of data that makes you like particularly identifiable in the database. So advantages of using differential privacy is like your system is protected from any kind of information. Hence, the goal of attacker is irrelevant. He doesn't need to, even if he breaches the database, he won't be able to find who you are. And it works no matter what the attacker knows about your data. Like even if the attacker doesn't know about your existence, your data is still protected. So it's not on a what you call cause effect situation. It's already protected from way before. So, so the setting used in this project is something called a local differential privacy. Now, why this is important is because when you talk about privacy, it's something that users should have complete control of. So our system is basically implemented right at the end of the user. Like user sends a data, true data, it goes through the system, and the system sends to the aggregator. And every single user has its own fine-tuned system so that they have full control of what data is being sent. This also enacts the fundamental power of privacy. So let's go straight to the implementation. So the main module in the implementation is something called the proxy random responder. So that's essentially a local differential private system that sits between the user and the data aggregator. So the data aggregator asks a question, the user responds to it, and that response is sent to a proxy random responder, and the proxy random responder randomizes the response and sends it back to the data aggregator. So so the algorithm involved in proxy random responser requires three inputs. First is the set of questions that the data aggregator wants to know about, and set of possible answers for a particular question. This project is actually limited to the scope of categorical and ordinal data. So that's why it's clearly defined what a set of answers a question would have. And the true response, which is a set of definite answers to particular question. So like question one would have A1 as the answer, question two would have A2 as the answer. Uh, so given these three inputs to the proxy random responder, it does the following computation. First, it computes like the distance between the actual set of values to other set of values. Like you can consider this as, like every possible answer to a set of questions in a vector space, and, finding out the distance between them. And this distance is called the budget. So the higher the budget, the farther the answer is to the true answer. And the second thing we do is we group the responses based on budget. So like we bin the responses into something called levels, and these levels are used to generate this special tree, which uh, which on parsing that tree gives you a random response that satisfies the epsilon differential privacy condition. So an example of the tree would be, let's say we have what you call levels of 0 to 4, where obviously a response of budget 0 means the true value. And these nodes L1, L2, all the way to L4 are basically just a random generator with coin flip probability. So parsing of this tree would be me giving out a true response to L1 node, and L1 node does a coin flip probability, and if it returns a head, it responds truthfully. But if it returns tails, it does this coin flip again, and then if that coin flip returns a head, it goes to the set of responses of budget one and picks one at a random. So imagine if you have like four responses, it picks one at a random uniformly. So uh, this is like the main component in proxy random responses. So we'll see how this tree actually ensures that our whole algorithm is differentially private. So let's consider two questions with A1 with a Q1 and Q2 with answers A1 and A2, and these are like the possible set of answers A1 to D1 and A2 to D2, and the true answer being A1 B2. So so when you do a distance, when you do this vector space budget calculation, you'll see a matrix of this form where budget one has two responses and budget four has one responses, and so on. So taking this, and when you build the tree, it's same as the tree that's mentioned over here. Since we have like 0 to 4 different levels, so the tree form would be like this. So let's take a particular query like A1 and A2. According to the equation above, the probability of given my truth being TR and response being TR, the response being truth is 0.5 because of one coin flip over here. And then if the system responds, let's say A1, A2, so its probability with given truth is 0.125, and that would be because it's on the level one. So first coin flip giving out a tail would be 1/2. Second coin flip giving out a tail would be giving out a head would be 1/2. And since there are two responses here, the probability of picking at random would be 1/2. So 1/2 to the power 3, that's 1/8, that's 0.125. So the ratio between those two equals to 4. So this, upon putting that 4 number in our epsilon differential privacy equation, we prove that our system is ln4 differentially private, which is well under the limits. So let's look at the results. Like the results will actually give a better understanding of why we decided to build the tree. So so this is on a set of this is like on a database which had like two queries, and one had a set of five possible answers, the other had a set of 10 possible answers. And upon running this on 600 different queries, this is the kind of the histogram that's formed. So the blue one is the true responses, and the what you call the brown one is the randomized responses. So one thing that to be noted is, like whenever I try to randomize a response, the obvious question would be that wouldn't it harm the trend of the data we are collecting? But my algorithm here has shown that the trend of the histogram that's plotted here has varied slightly, but not to a higher extent. So which means upon collecting from 100 different users, you still manage to preserve the trend of the data, and also making sure that every user has their privacy respected using the algorithm. So that's essentially what's stated over here. So if histograms trend is saved, so as will be all the statistical measures such as mean, median, and mode would be saved. So and another plot of it would be this. So the histogram on the top is the true response, and the histogram on your right is the randomized response. So If I were to give every single true response to the system, the kind of hexagon plot that you see over here would have been in a diagonal fashion. But you see that at response one, there's like a higher variation of hexagons with some denser parts. So that's actually like a what you call contradiction that needs to be proved. So which is basically, since the result from the set of predefined data, we already know the histogram that followed by adding randomization claims the fact that more response category would have higher variance, but in reality, differential privacy holds for any set of responses. That's what I want to enact. Like when you compare this with the previous one, you'll get through it. So, and one last thing, the reason why we choose this tree is there's like much lower probability for the system to give a response of budget tree. So higher the budget, the less likely that's been sent to the server. So that's like the three main important parts of the tree. And the conclusion from the experiment is it has included randomization, and the mean of error between the true and random values is close to 29.42, which is subject to change. Like there's a higher lower limit to it, but it is well within, like since we have proven that the trend doesn't change to a higher level, so it's well within the limits. So so the future work to this would be what you call modifying this to process numeric data, because this only works for categorical data right now, and implement it as a web browser plugin, so that whenever you go to a survey page, you can choose to what you call respond by respecting your privacy. And the last and the interesting one would be, like at this moment we only talked about the user randomizing response, but the data aggregator doesn't know to what extent the user has randomized response. So we can actually make these systems aware of the kind of randomization the user has chosen to randomize his data with. So the aggregator would at least know a range of possible values on which it has to tweak its analytics algorithms. So and that's all about it. Any questions?